So in this session, we are going to look at intensity-based meta-analysis that I will use as a synonym of image-based meta-analysis. And so first, I would like to start by going through what's the difference between a coordinate-based meta-analysis, which is the approach we've been mainly talking about until now, and an image-based meta-analysis. So here you have your typical neuroimaging experiment where this is really a rough overview. You're going to draw an experiment, do some acquisition where you get a bunch of raw data. On this raw data, you perform a statistical analysis, you get some results, and hopefully you get to publish these results. Of course, here we are interested in meta-analysis, so we are not looking at one study, but a group of studies. And what we typically do is to rely on the data that is available in the scientific publication in order to perform this meta-analysis, which is therefore called a coordinate-based meta-analysis because we are combining those X, Y, Z values that are available in the papers. And this is combining very sparse information, those peaks that we have in the brain. But if instead of relying only on the paper, we could go one step before and have access to the statistic maps that were produced as an output of each study. And I'll go into more details later as to which statistic map we might want to look at. Then what we could do is an image-based meta-analysis. And here we are combining values in each and every point of the brain for every study. So it has been shown that coordinate-based meta-analysis is suboptimal compared to image-based meta-analysis. And we can just illustrate that, think of a very simple example. Let's think about sub-threshold effect. So let's say we have an effect that is low. It might not be detected by any study. This means that in a coordinate-based meta-analysis, you won't be able to detect this effect because it's not reported. But if you have an effect that is sub-threshold but consistent across your studies, when you do an image-based meta-analysis, you might be able to detect this effect. So the question now is how can we perform this image-based meta-analysis, and what do we need to be able to do to perform this kind of approaches? So to perform an image-based meta-analysis, we can use an approach that is very similar to what we do for group fMRI analysis. So here we go back to one given subject. So you have some preprocessed data. You fit a subject-level model. You get contrast and standard error estimates. And then those can be combined to get a statistic that we can threshold to get the areas of significant activations or no activation. Typically, in a study, we have several subjects, and when we want to combine the subjects to get results at the group level, what we do is that we do not combine the detections themselves, but we go one step before, and we combine this contrast and standard error map into a second-level model, which can be a group model, which can be a between-group model, and so on. And on these second-level contrast map and standard error map, we can build a new group-level statistic that we can threshold to, again, get the significant areas of activation. For meta-analysis, we can do something very similar. So here, instead of having just one study, I have a bunch of studies. And again, I can go back to the contrast and standard error maps for each study and combine them into a third-level model in order to get a third-level contrast map and a third-level standard error map that I can threshold to get my inference. So the gold standard approach is to perform a three-level general linear model. You have your first level, the subject level, your second level, the study level. These are the two levels you typically have in your neuroimaging study. And to do our meta-analysis, we just add a third level, which is the meta-analytic level. And the gold standard statistical approach to do that is a mixed effect general linear model in which we are going to combine the contrast map, but also the standard error maps that provides us with information about the accuracy of each contrast map for each study. in order to be able to use this approach, we first need to have access to these maps, and we've already said several times during this session that, well, this data is rarely shared, so that's the first issue. But even if you have access to the contrast map for each study, you also need to be very careful that these contrast maps are expressed in the same units. And I'm going to here give a bit more details about what we mean about the same units. So here we have one of our statistical analysis where we are going to, on preprocessed data, fit a model, and then get our contrast and standard error map. But in fact, we don't have a single step, but several steps, and each of them is going to impact the units of our contrast maps. So the first step of interest here is data scaling. Because when we work with bold fMRI signal, we have a signal that is non-quantitative, what we usually do is that we scale the data to % bold signal change. And when you do that, you basically change the units of your data. And the units are going to depend first, of course, on the target that you are setting, but also on the way you are estimating the mean signal in your image. And this, in turn, depends on how you define within your image what's background and what's brain. And this is done differently in different software, for instance, in SPM and FSL. And this means that the scaling will be slightly different. In terms of target, it's good to know that SPM scales to 100 and FSL scales to 10,000. So we need to compensate for that when we combine contrast maps that were performed using different software. So that's the first step. Then second step, we usually fit a model, and the units of our parameter estimates are going to depend on how we define the design matrix. So how we scaled our exploratory variables in this design matrix. So usually if you have a block-related design, you're going to be fine. But if you have an event-related design, then you will have to perform special care in order to make sure that your units stay the same. Then finally, usually we are not interested in just one parameter estimate, but in a linear combination of parameter estimates. And the way you define your contrast weights is again going to impact on the units of your contrast maps. So for instance, if I was looking at a contrast vector of 1, 1, 1, 1, or 1 quarter, 1 quarter, 1 quarter, 1 quarter, I would get exactly the same results for my study. I would get the same statistic map and the same p-values. But if I look at the contrast map, they are going to be scaled differently, and this will impact future meta-analysis. So as a rule of thumb, we say that to define your contrast vector, it's good to keep the sum of the positive element to 1 and the sum of the negative elements to -1. So just to recap, the gold standard approach to do an image-based meta-analysis is to use a third-level mixed effect general linear model. But to be able to do that, you need to make sure that all your maps are expressed in the same units, and units will depend on the scaling of your data, the scaling of the predictors, and the scaling of your contrasts. But crucially, we also need to have access to those contrast estimates and to those contrast standard error maps. And in fact, it's true data is rarely shared as a support of a study, and sometimes we have some statistics that are shared, but those are not the contrast and standard error maps. So here is a table of other types of data that could be shared and are sometimes shared. So sometimes we also see statistic maps being shared, either the equivalent Z statistic, or this could be a T statistic map with the corresponding degrees of freedom. And another case, we could also have the contrast maps, but not the standard error maps. So in this table, you see examples of like file names for SPM, FSL, and AFNI for those different types of files. And in the following, I'm going to describe different approaches that we can use when we have these different types of maps available. What type of image-based meta-analysis can we do? So first, if I only have Z maps, there are approaches that allow me to combine the p-values, which we can easily derive from the Z maps. We can do a statistics that corresponds to the average of the Z-maps rescaled so that we get a standard normal distribution. Or if we want to allow for some between study variance, because the first two approaches are fixed effects, so they assume that we have a between study variance that is equal to 0, then we can do a one-sample t-test on Z-maps. If you have the Z-statistic maps and the sample size for each study, we can use a weighted version of the Stauffer's approach where you are going to assign a weight for each study which is proportional to the square root of the sample size. So basically, you're giving a bigger weight to the study that had more subjects because you think that you get more precise estimates because you had more subjects to pull from. Then if you only have the contrast maps, what you can do is to perform a random effects GLM. So this is very similar to what SPM is doing at the group level. So typically when you do a second level analysis using SPM, you're going to combine your contrast estimates from all your subjects. You don't bring the standard error maps at the second level. You can do the very same thing for meta-analysis. And finally, you could also, even if you have the contrast map and the standard error map, do a fixed effects version of the meta-analysis, where you're going to ignore between study variance. In terms of implementation, how can we actually perform this method? So the gold standard mixed effects approach that use the contrast and the standard error map, the one we looked at the very beginning, is implemented in FSL using FEAT. In SPM, there is the SPM MFX option, which is since SPM 12 available now in the batch system. And in AFNI, you have 3D MIMA. If you want to perform a random effects GLM, where you only use the contrast maps, then in FSL, you can use FEAT again with the OLS option. In SPM, this is the default approach at the group level. And in AFNI, you can use 3D t-test. The Stauffer's random effect is basically using the very same tools, but with the Z-statistic maps as input. Finally, the other approaches that I've presented are not currently implemented in the main neuroimaging software. We have a toolbox that is available, but it's still in beta, but we would be very happy to get feedback if you would like to use it. So this toolbox implements those Z-based approaches I presented earlier. And on this slide, you see an example of image-based meta-analysis, which was performed on a set of 21 studies looking at pain. And on the left side, you can see methods that are random effects. And on the right side, you see the methods that are fixed effects. So basically, assuming that we have no between study variance. And so the method on the far left is our gold standard, the mixed effect GLM, and you can see that we get very similar results with random effects GLM, which is very similar to what was shown for group fMRI, because here we're looking at a one-sample test. And then, on the other hand, all the fixed effects approach are quite similar to one another, and they are more sensitive, which is expected because, again, we are ignoring this between study variance. So I've been through all these different approaches that you can use for image-based meta-analysis. And to finish, I would just like to outline how you can share your statistic maps if you want to. So we've already talked a little bit about NeuroVault, which is a website where you can go and upload your statistic maps. And for those who are not familiar with NeuroVault, this is an example of collection. So a collection on NeuroVault is just a group of images. You can choose which images belongs together, and you can upload as many images as you want using the Nifty format. Then you add a title for your collection, and you can link to a paper if you have a manuscript describing this data set, or you can leave this empty and just have it as a collection that you can share with other people. If you want to go from SPM and FSL and upload your maps on your Vault, you can either just go into, for instance, the SPM results folder and pick those Nifty images, so the contrast images, the T-stat images and then upload them to NeuroVault. Or you can use this export that we've created, which is called NIGM results, which is a zip archive in which you're going to have all those images, so the statistic map, the contrast standard error map, which is computed for SPM but not available by default, and a number of metadata, as much metadata as possible describing your experiment, some information about your design matrix, and so on. And there is also a tool to go from FSL to this NIGM results archive. And then on NeuroVault, you can directly upload this NIGM results, and NeuroVault is going to look at the metadata in there, extract it, and extract all the images. So in conclusion, when data is available, image-based meta-analysis should be preferred over coordinate-based meta-analysis. In practice, it can be difficult to do a mixed effect GLM because of the issue of units, and if you want to make sure that all your studies are expressed in the same units, you need to have a lot of information about the original studies. When only the contrast estimates are available, the random effects GLM is a good approximation. There are still a few tools for Z-based meta-analysis, but they are still underway. And finally, I would advocate for data sharing tools such as NeuroVault, where you can share your maps so that tomorrow we can all do image-based meta-analysis. Thank you very much for your attention.
And JB has a question. And Camille, can you repeat his question once he says it?
Okay. Okay, so the question is, could the process to go from the standard neuroimaging tools to NeuroVault be even easier with just a button? So to answer the developer part of things, I think this button is coming. I think it's available in SPM, but still a little bit hidden, but probably if we ask on the mailing list, will tell us where it is. For FSL, the tool is now available, I think, as part of the latest version of FSL. It's not a direct upload to NeuroVault yet, but this is something that is under discussions. And as to how we can convince people to go and push their data, I think it's an open question.
What's the incentive?
The question is, what's the incentive? Peace, harmony, and open data.
Image-based meta-analysis, of course.
Yeah, but let me take the devil's advocate position here. There's going to be some people that are easier to incentivize to do that than others. And one could argue that any image-based meta-analysis based on NeuroVault will be intrinsically biased because it's basically based on the data from original data from those people that are into open science. Isn't there a fundamental bias potentially that's creeping into NeuroVault then?
I think the easier the tool is, the less bias it's going to be. But of course, the more steps you have to do, the more convinced you have to be that this is the good thing to do. Yeah.
One quick question.
Are there options for activation-based, intensity-based meta-analysis on the surface?
Just to restate the question.
I don't think so. I mean, we could use
the question
SPM.
is whether there are options for surface-based meta-analysis. Way back when David Van Essen, I thought, had a tool a bit for coordinates on the surface, but I'm not aware of any tool right now.
Well, coordinate-based, it doesn't make... I mean, image-based, it's possible. Coordinate-based, it's tricky, because the problem is you do have a lot of spatial uncertainty just by people using different templates, summarization approaches, and so on. And if you do it on the volume, then basically being off by 2, 3, 4 millimeters isn't so bad. Surface-based, you can actually jump to a different lobe easily. And so in the end, for coordinate-based meta-analysis, surface-based analysis would make things worse, most likely.